So let me ask you something. What if the darkest, most mysterious objects in the entire universe actually glow? We're about to dive into one of the biggest, most mind-bending puzzles in modern physics, Stephen Hawking's black hole paradox.
Right, this is the image we all have in our heads. A black hole is this ultimate cosmic prison. It's got so much gravity that once you're in for good. Nothing gets out. And for the longest time we thought, well, that's the end of the story.
But what if it's not the end of the story? What if these cosmic prisons aren't actually eternal? You know, this one little question completely upends everything we thought we knew, and it opens a door to a reality that is, frankly, a whole lot stranger.
Okay, so to really get why this is such a huge deal, we first need to understand the old-school classical view of a black hole. For decades, the physics was pretty straightforward. A black hole was a one-way street. Anything that crossed its border was just gone, lost to our universe forever. And this point of no return, it's got a name. The event horizon. Now, it's not a physical surface you could, touch or anything. It's a boundary made of pure gravity. The moment you cross it, the speed you'd need to escape is faster than the speed of light. And since nothing is faster than light, well, you're not getting out.
But then, 1974 happens, and that whole classical picture just gets shattered. A young Stephen Hawking asked a pretty simple question. What happens if you apply the weird, topsy-turvy rules of quantum mechanics right at the edge of a black hole? The answer he found would literally change physics forever. His conclusion was so simple yet so unbelievably profound, it honestly sounds like something out of science fiction. He found that black holes, they aren't completely black. They have this faint, almost invisible thermal glow. Against all odds, they radiate energy back out into space.
So how on earth is that possible? How can anything escape that inescapable gravity? Well, it all comes down to a process that you can really only describe as a quantum heist, and it's happening constantly, right there at the edge of space and time. So to understand this heist, we have to look at what we think of as empty space. Turns out, quantum mechanics says it's not empty at all. It's this bubbling, chaotic sea of virtual particles. They're constantly popping into existence, a particle and its antimatter twin, and then in a flash, they smack into each other and annihilate. Poof, gone. So here's the heist. Imagine one of these particle pairs pops into existence right on the razor's edge of the event horizon. The black hole's insane gravity can literally rip them apart before they have a chance to destroy each other. One particle falls in, but its partner gets flung away, escaping out into space. And from our perspective, way out here, it looks like the black hole just spat something out. Now, for the universe's books to stay balanced, there's a neat little trick. The particle that falls in is considered to have negative energy. So it actually subtracts a tiny bit from the black hole's total mass. With every single particle that escapes, the black hole loses a microscopic amount of weight. And this steady stream of escaping particles, that is Hawking radiation. Okay, so think about that for a second. If a black hole is constantly leaking mass, even at this impossibly slow rate, well, that leads to a really staggering conclusion. It means black holes aren't eternal. They have a lifespan. They will eventually die. And here's where it gets even weirder. The temperature of this radiation has this bizarre backwards relationship with the black hole's size. A gigantic, supermassive black hole is actually incredibly, incredibly cold, so it radiates super slowly. But a smaller black hole? It's much, much hotter, and it evaporates way faster. And just to put this into perspective, the Hawking temperature of a black hole that has the same mass as our sun is about 60 times billionths of a Kelvin. That is colder than the background temperature of deep space itself. Which means that right now, big black holes are actually absorbing more energy from the universe than they're giving off. But give it time. And I mean truly cosmic amounts of time. Trillions upon trillions of years, long after the last star is burned out. Over that timescale, they will have radiated away all of their mass. And as they get smaller, they get hotter and hotter and hotter until they finally disappear in one last brilliant flash of energy. So Hawking solved one huge mystery. Black holes aren't forever. Awesome. But in doing so, he accidentally created an even deeper, more troubling paradox that physicists are still tearing their hair out over today. It's called the information paradox.
Okay, here's the problem. Hawking's math showed that the radiation coming off a black hole is thermal, which is a fancy way of saying it's completely random. It carries zero information about what fell in. A black hole that ate a star would radiate in the exact same way as one that ate the same mass of, say, encyclopedias. But this breaks a sacred fundamental rule of quantum physics, which says that information can never be destroyed. These two pillars of modern physics gave us two completely opposite answers.
And think about what we mean by information. It's the unique quantum fingerprint of every single particle that makes up a star, or a planet, or even a book. So if you toss that book into a black hole, and that black hole eventually fades away into nothing but random heat, where did the information that made up that specific story go? Was it just deleted from the universe?
And that, right there, is the heart of the information paradox. Hawking proved that the universe's ultimate prisons aren't eternal, but he left us with a much deeper question. If the story of an entire star can be completely erased from existence, can anything truly last? The answer is still out there, somewhere, hiding in that faint glow at the edge of a black hole.